Hello, everyone. Thank you so much for being here. My name is Linda. I'm the project manager of this Agentic AI Summit. Thank you so much for coming here, joining us on a Saturday, out of your busy weekend. We understand, we just want to appreciate you guys coming over here and beating the traffic. We understand Berkeley is a little bit far out, compared to the other areas of the Bay Area. So thank you so much for coming here. We're starting the program right now. And I want to do a quick introduction of Berkeley RDI and then the summit and then the program for today for the Frontier stage. And then the session chair, Xiangding, will introduce the speakers for the first session, Agent Architecture and the Systems. And then we'll get started with all the exciting presentations and talks. Thank you so much. So today at the Frontier stage, we have a lot of industry leaders, primarily product and research leads from the top tier AI companies in the space. And we have 5 sessions: agent architecture and systems. We have AI for science. We have agent applications. We have AI security and alignment. And then 1 second, I think I forgot the fourth session. The foundations of agents. And in between those sessions, we also have very, very interesting lightning talks. And then we also have poster sessions, which will be lined up around the edges of this tent. And this afternoon, around 1:45 p.m. or 2 p.m., we'll do the award ceremony of Agent X and the LM Agents MOOC Hackathon. The winning teams will do the award ceremony, and then they will also do some presentations, talks during that session as well. So it's gonna be a very packed, very exciting program for the whole day at this stage. Thank you so much for being here again. Looking forward to the exciting discussion and looking forward to navigating, marching into the future of agentic AI. So without further ado, let me introduce the session chair, Xiangding, who will introduce the speakers of the first session, Agent Architecture and Systems.
Thanks for Linda's introduction. Okay, so the first speaker is Ranjan Sinha, right? So Ranjan Sinha is IBM fellow and CTO, IBM Research AI, and he will introduce the talk about natural language interaction protocol, or universal application level protocol for the age of general AI. So let's welcome Ranjan Sinha. Yeah.
Okay, good morning. Great to be here. So we have trained AI models using the entire internet to speak in fluent natural language. But when it comes to AI agents talking to each other, we are still stuck with rigid and brittle approaches because they are based on predefined schemas. So what if agents could communicate with each other just the way that we do using plain language? Just like HTTP unified the web, we are on the verge of a new standard for agents that is based on natural language itself. So the original work on the natural language interaction protocol, which I'll refer to as NLIP, it started in March of 2024. The ECMA technical committee was formed in December of 2024, and ECMA is the body that standardizes application-level protocols. So I'm representing the ECMA technical committee and the NLIP collaborators in this session. So researchers from industry and academia are helping to design a universal and open protocol that is based on natural language. Now, today's systems use several application-level protocols and APIs with rigid schemas, and it causes challenges in integration, interoperability, and version management. So the question is, could we apply the generative AI technologies to design a more smarter and adaptable protocol? So if you look on the bottom left, that's the traditional protocols, where you have agent 1 communicating with agent 2, and you have the message structures A and B. They all need to be the same, and as well as the one that is over the wire, that's P, right? Because predefined schemas, they all need to be the same. In contrast, the NLIP, agent 1 message structure doesn't have to be the same as the message structure for agent 2, that is B. And you can use generative AI technologies to translate between the structures. The only important thing is that the meaning itself should remain the same. So that's I would say, the essence of the idea. So NLIP provides a simple, open, standard, and common protocol for applications, agents, and services to communicate with each other and to us. It does assume generative AI capability at the endpoints. It follows a multi-turn request and response paradigm to ensure that the meaning is refined and well understood. And some of the obvious requirements for the protocol has got to be secure. It should enable various safeguards, such as data privacy, data usage policies. It should be implementable across various underlying transports and API styles. It should support multimedia content, should be efficient, should be implemented in various languages, and should be standardized in an open forum. So NLIP uses generative AI for structure-independent communications. And as I just touched upon that in the first slide, all the three structures must be the same in a traditional protocol you see on the top right. And that forces a rigid API. There could be version upgrade issues. It limits extensibility. And there is tight coupling between the systems. NLIP allows structure independence. And you'd find that the structure for these messages are different or can be different. And use generative AI because it's really good at passing unstructured text to structured text. And it has really worked in practice. We have done quite a few POCs and reference use cases, and it's panning out pretty well. And of course, the more we do, the better we understand it, and we can update the specifications accordingly. So the scope for NLIP is currently it's communication between two AI agents within and across organizations, or between humans and AI agents. Anything that is legacy software or pre-AI or pre-Gen AI, that's out of scope. Now, there are several multiple single vendor protocols that have been proposed for various aspects of agent tasks, resource management, tool calls, and discovery. Some of the popular ones are the Anthropic MCP, IBM ACP, Google A2A, Cisco Agency, and several more. So NLIP can interoperate with them in two ways. Mode A, where NLIP can be the northbound API, and the single vendor protocol, the southbound API, and use the LLM to translate between them. And in mode B, the NLIP provides the interoperability across the different domains of single vendor protocols. And each domain can have multiple agents using different agent frameworks. And we have done some POCs that have panned out pretty well. But we believe that eventually, the industry should converge to an open standard protocol such as NLIP, or at the very least be influenced by it. Now, this is very similar to what happened in the early 1990s. All right? So every business app had its own protocol. Custom client, bespoke integrations. You had several pre-HTTP protocols. But once HTTP was introduced and was widely adopted, and under a single general purpose interface like the web browser, it really simplified application delivery, interoperability, and unleashed the potential of the internet and commerce. Today, we have a fragmented ecosystem of AI agents, tools, APIs, and proprietary integrations. LLMs and AI agents don't all talk the same language. AI agents and chat are becoming a common interface for business solutions. So if you can define that single standard protocols, HTTP for intelligent agents, it can really unlock and unleash the scale and collaboration of agentic AI applications. This is the NLIP schema. As you can see, it's really simple and concise. This is it. And you can check this out at our NLIP project on the GitHub page. And I'll provide some links at the very last slide as well. So let's dig deeper into the message structure. I've highlighted the content field because that is really the key field. The rest are supporting metadata. So the basic structure of a NLIP exchange is a submessage. So the format stores what kind of content that you're sending. Is it text? Is it JSON? Is it image? Is it video? The subformat is a bit more of information on the format. So if it is text, what language it is. If it is image, what is that encoding that is being used. And the content is the actual message. So in this case, let's say, what is the weather in Berkeley tomorrow? Label is a simple name or tag, weather info, for instance. So nlib message can consist of a sequence of submessages, but in most cases, a single submessage suffices. And I have a use case later on that talks about how we have used this submessage field as well. Right? It's really simple. Now, this message format is community-driven. So we are all, the researchers are coming together to define this structure, and it aims to solve the Tower of Babel problem in agent communications. And you find all of these other protocols defining their own message structure. So the salient features is the primary mode of interaction is natural language. It could be typed text or spoken text, which you can convert using speech-to-text conversion, and we have a POC that has worked out really well. It supports vision, audio, and other modalities. Structured text is also supported, but that's not the primary means of communication. There is no need for custom configurations. Your configuration and policy exchange are all done via natural language. And you can use different AI models at the endpoints. We have experimented with OpenAI models, Gemini models, Claude, IBM's Granite models, and they've worked out pretty well. Now, nlib is not reinventing the wheel. It builds on tools and technologies that's already widely being used. So it runs on top of secure connections like TLS, runs on top of the authentication system, uses the base transit protocol like HTTP, and on your cell phone or computer, the nlib library can talk to the nlib server, which then talks to the business application servers for ordering, scheduling, or anything else. So the key message here is the nlib integrates seamlessly with existing system architectures and doesn't reinvent the wheel. So let's look at an example. So for the next few slides, I have a few examples that will make this a bit clearer. So Agent A is trying to introduce itself to register. And there is a version mismatch between these two endpoints. So Agent A sends a message, I am A running on URI-EU. Register interprets that and creates a structure. It has an idempotency field, and it didn't find that information in the message. So it marks it at X. And then tries to clarify with Agent A, are your operations idempotent? And Agent A responds back, I cannot interpret your message, which indicates that it doesn't support it, and Register smartly assumes and identifies that as idempotency is not supported, so it's false. And it may reconfirm that you are A with URI-EU and do not support idempotency, and it confirms back as that is correct, right? So this is a request and response to ensure that the meaning itself is refined and well understood. There's another example where it's a chat interaction, probably one of the most popular use cases. And this is, so the chat client inquires about the ECMA organization. So it uses the format text, subformat is English, and has the content, what is ECMA? The response from the chat server, again, format, subformat, and the content, and content provides the response for the question. And of course, there are few other fields which I've omitted. It's not as relevant. And you can find these examples in the link I provided. That's in the nlib project page. It's part of the specifications. This is the use case that walks through a federation amongst various agents. So the client sends the same question to the proxy server. The proxy server then sends this to the three agents, agent 1, 2, 3, that may respond back with three different definitions of ECMA. The proxy then combines the responses and then uses the submessage field and sends it to the integrator app to requesting that it integrate this, synthesize this, and provide one response, and which it does and responds back to the user. So this is an example how you can use the submessage field. In this use case, nlib has been shown to work with popular agentic AI frameworks like LangChain and Llama Index. And it also supports tool calling using standard protocols like MCP. So in this case, you have a weather chatbot where the coordinator agent that is based on the LangChain receives a user query and delegates tasks to a worker agent that is based on the Llama Index, which then accesses an external weather API using MCP or other protocols. The coordinator then aggregates the responses from this task and then returns a synthesized answer to the user. And it shows how NLIP can work across agent frameworks and uses existing protocols. There's an example, a speech-to-text, where a customer communicates the intent using speech. We use an NVIDIA ASR model to convert the speech-to-text, forward that to the channel recommender agent using NLIP over HTTP. The channel recommender finds the most relevant Reddit channel. This is a Reddit search, a Reddit channel, and then forwards that information to the search agent, which finds the most relevant or the most recent messages in each respective Reddit channel, and then stores that, caches that in the Redis database. And this is an example of speech-to-text, and that's also worked out pretty well. So key takeaways is that NLIP is structure agnostic. It is not tied to any predefined schema. It allows flexibility across diverse data formats. It's natural language centric. You can consider this as an envelope protocol, and this will enable cross-protocol communication. And it's built for generative AI, and it supports use of LLMs to translate or mediate between different message formats. And it's simple, concise, open, and standardized. So the next steps and the status. Currently, NLIP is being defined and standardized under the ECMA TC56. The draft specification initial implementations are in our NLIP project GitHub, QR code on the top right. And we do welcome your comments and feedback. These are still very early days for protocols, so it will really help. And if you're interested in supporting in POCs, that's also very welcome. We are targeting a formal standardization in the second half of 2025. So if you'd like more information, wish to get involved, please visit this NLIP GitHub page and contact us using this email address. So with that, thank you very much. Okay, cool. On time? Excellent.
Okay, thanks for Ranjan's great talk. So let's go to next speaker, Debo Dutara.
Thanks. Sorry for the delay. There was a problem with the slides. They have a PDF instead of my slide deck, but we'll try to keep it simple and safe, hopefully. So if you think about as a show of hands, how many people are from academia? And industry? Mostly industry. So that's good. Because what I wanted to kind of talk about is, as you are looking at different architectures for building agents, so let's imagine that multi-agent is going to be the common design pattern for enterprise applications, maybe in a year or two. It's still not there, right? And a year or two is actually being very, very optimistic. So this is your new workload, a swarm of agents. Imagine a new enterprise with 100 agents running alongside, human workers. Basically, my swarm of digital minions, right? So now the question is, where will these agents run? Most people think today it runs in the cloud because that's where we are running all these agents today. There are these platforms, and these mega companies like OpenAI, Anthropic, Google, they're just running everything in the cloud. But that's today. But what we see in the enterprise is that it's going to run anywhere and everywhere, right from your shop floor to a battleship, submarine, all the way to your distribution center in case of retail. So the question is, how will you actually build these agents? How are you going to choose the models? How are you going to choose the systems and the entire stack? And now for an enterprise IT, this is a huge problem because now you've created multiple stacks, multiple systems that they have to manage, and the InfoSec, the security officer, is also challenged because you have to then define the security policies of everything. For people who work in the industry, you know how tightly controlled these systems often need to be because the data has governance rules, especially for certain workloads like in banks, healthcare, data cannot often leave certain guarded walls. So we believe that one needs to have consistent technical architecture for running these agents. And so the question is, how do we design the next generation enterprise AI systems, not AI systems? Because AI systems in the research community, in the open source community, are sprouting like mushrooms, Cambrian explosion. Of course, there'll be consolidation. So in order to design systems, you go back to distributed systems, right? You go back to the basics of hardcore system theory, and think about CAP theorem, where you see that only two of the three properties of a distributed system can be true, between consistency, availability, and partition. Now the question is there something like this for a multi-agent system? Because why? Because a multi-agent system is also a distributed system. So that's the kind of question that we have started asking within our team in Nutanix AI. And then one of our engineers, I don't know if he's here, Janan, so one of our engineers came up with a conjecture. It was a claim that maybe there is a CAP theorem, indeed, for designing distributed agentic system, and we called it the bar theorem. And because it was a fun talk, we actually said, let's go and have, most of us go to a bar and decide on a napkin what we need to do. So we called it a bar theorem, which is essentially the three dimensions are budget. So how do I respond? How does an agent or an LLM, even an LLM, respond within a particular latency and with a particular compute budget? So that's your budget and authenticity. So how do I know that the retrieval? So let's imagine a compound AI system, which the term was founded over here in Berkeley. A compound AI system is retrieving information. How do you know it's not hallucinating? What's the accuracy level? And then reasoning. So in reasoning, we are looking for human-like chains of thought that are logical. So now, if these are the three dimensions, we claim that any Gen AI system or multi-agentic system can prioritize at most two of the three aspects. And this, obviously, it's a very tall claim. So from within our team, a bunch of us got together to kind of, as computer scientists, when you want to prove a tall claim, you start with smaller claims. And so we have some initial results that we are soon going to be in ArchiveX, where we've actually shown that for certain scenarios, this is actually true, using formal mechanisms. So, but over here, let's look at the bar theorem in real life, right? So if you think about enterprise AI, most of the common use cases, 90% plus use cases, basically talk to my data. Talk to my data, talk to my code, talk to my data warehouse, talk to my time series. And that's basically, you want cheap retrieval, you want less hallucination, because you don't want data retrieval or a query system or a RAG tool give you false results. Then you want to take an action, you want auditable trails, and you want some kind of reasoning, mild reasoning with some small LLMs, and you want it to be cheap too, right? So there are these RPA agents and a bunch of other agents where you can build pretty much with open source small models today. But they may not be very highly accurate for retrieval. But then there are these large compound AI systems that we all know about, deep research agents, coding assistants, and very complex video generation, which is pretty good. But the price that we pay today, somebody's subsidizing it today. When we all have to pay for the ChatGPT and the Anthropics of the world, and there has to be a P&L budget associated, I think the cost will be much more than it is today. Unless this community can design very, very cost-effective solutions to bring down the cost by 2 orders of magnitude, it's going to be hard. So our claim is that this bar theorem is going to be true in real life for a while. Now, if you think about an enterprise, look at a bank, a hospital. We all have to go to a hospital. We have to go to a retail store. When you want to design agents that run all the way from a retail store to a packing distribution center to the headquarters, data centers, and in the cloud, if you look at every data scientist today, they all want 4 to 5 LLMs to build an agent. It's not just one LLM, right? You need an embedding endpoint, you need an inference endpoint, you need re-rankers and guardrails and so on and so forth. So if you look at an entire cost to the enterprise, the TCO is astronomical. And most of these data scientists today, including in my own team, a bunch of them are here, everybody loves to run VLLM, again from Berkeley, or pick your favorite inference endpoint in a container and just run it and not have to deal with any other thing. Like, I just run it on my laptop or running it on Olama. So that is what's happening today. But what the IT departments of enterprise is petrified and paranoid, because it just leads to a huge problem with security. It's complex to manage, the security risks, it's just expensive. So our strategy for at least, with the budget part of it and complexity part of it, is to kind of shrink everything down into shared enterprise grade endpoint management and consistent architectures, starting with Kubernetes. We've internally inside the company, we've standardized on vector databases using open source. Basically, everything is open source, using Postgres, PG Vector. So we have an entire stack that we use to run multiple agents, and the agents can come from with any kind of tool chain, and you can have any kind of communication protocol. That's for us. The technical community will figure it out. For me, the first thing is, how do I manage the costs? How do I make it easy to deploy? I partner with my CIO to make sure that we can do this inside the company in a simple, secure, and efficient manner. I'll end the talk with a couple of non-technical stuff, which is very important as you design systems. There are 3 dimensions of AI, at least in Nutanix and in most enterprise companies that I talk to, are people, tech, and process. Of course, this conference and most conferences and the entire valley is focused on the tech, which is the right thing to do. But when we look at deploying these agents in actually enterprise companies, banks, hospitals, companies like Nutanix, retail stores, people become a huge dimension, in the sense that we need to upskill existing employees to learn AI, to understand how to even deploy, even operate these agents. Because at the end of the day, autonomous agents are still going to be a thing in the future, right? Thing of the future. It's not happening anytime soon. So, and the other thing is processes. Today's enterprise already have fixed processes. We all love to, in this conference, want to talk about multi-agent systems, talking to each other using some protocol, but that's not how they will be deployed today. There has to be a change in processes. How do you show the ROI? Think in terms of, if you spend $1 million building and deploying agents, are you going to get $5 million worth of ROI? That's still an open question. And the other thing is that coming to an enterprise is not just engineering, right? A lot of people are very concerned. So you have the AI team that wants to do the cool things, the right tech, and then supposedly they are being slowed down, but it's not slowed down, because in a regulated industry, the IT comes in and says, you cannot run this wherever you want. You can't just run a VLLM container where you want. And then there's a legal team that says, how are you going to run this brand new model just popped up in a leaderboard, because I don't even know whether you can even use this. We don't know what the data provenance of that model is. So there are, again, 3 dimensions in an organization, and these 3 teams. So I'm usually in meetings with these 3 stakeholders, IT, the legal team, and the AI team, to figure out how do we change the processes that I talked about in this. And for each of this, is there a theorem that we can prove or a conjecture that we can come up with? How do we keep everyone happy? How do we show ROI in the enterprise while doing the right technology over here? Because we are all technical folks here. So anyway, the key takeaways is that multi-agent systems are going to happen. They're going to happen slowly, as you can see. 4 to 5 LLMs per agent, 100 agents. Think about this, LLMs are becoming small. They're getting better at reasoning, but you need to run these agents close to where you want to do your business. Maybe in the bank, maybe in case of military, somewhere else, right? In the field, battlefield. And you need to run agents close, and then you need to design these agents. They are distributed systems, so think about what are the real technical barriers. Where is the sweet spot for designing these agents? And manage your infrastructure sprawl. Don't think of that. Even as technical folks, think about when you're building something, how is this going to be managed, deployed, used? So I think with that, prioritize not just tech, but people and processes when you're thinking in terms of computer science. But I feel CS is a wide enough field. It's liberal arts today. You can actually apply computer science to all the 3 dimensions. And with that, thank you.
Thanks for Dable's great talk. So next speaker is Chi Wang. Yeah, Chi Wang is a senior staff research scientist at Google DeepMind. He will introduce MassGen frontier multi-agent scaling in open source. Okay, let's welcome Chi Wang for his talk.
Thank you. Good morning, everyone. Thanks for joining us at this Agentic AI Summit. This is the frontier stage, so I'm going to present a very new project, new open source project that's pushing the boundaries of the collaborative AI. How new is this project? It's just 7-day old. The first MVP was just out 1 week ago. So good luck with me. I've never presented a project as young as this one. In one word, this is a multi-agent scaling system that runs multiple agents, diverse agents, in parallel, sharing intelligence and refining each other's work. Okay, and you can check the GitHub from MassGen.ai link. And yeah, let's dive in. So if you have followed the recent breakthroughs from Grok Heavy or Gemini DeepThink, it's easy to see the inspiration. Harnessing multiple AI minds that tackle complexity far beyond any single model can do. Okay, there's a lot of recent exciting things about it, and the North Star is that we want to build co-evolving agents through collaborative interaction. So many of you have probably know that I've created this AutoGen open source framework since 2023. I've been working on IDEA and now AG2 for these multi-agent conversations. But many challenges still remain, and especially with the change of the new technology. In April this year, I wrote a blog post called Myth of Reasoning, and I talk about this thread of thoughts idea. And the key insight is that the human reasoning is actually much messier than what most people realize. So most of the time we have intuitive thoughts, and only after that we try to find justifications or find it's wrong and restart this process again. And but we need to make it cleaner for presentation, for communication, to convince others. So the nice chain of thought is not a it's not the start. It's the outcome of these massive processes, and by nature it's collaborative, right? So that's kind of one of the key insights I've been working on in the past few months, and recently I've seen real evidence in practice. So Graph Heavy and DeepThink, they prove that this is not just theoretical, it's practical and deployable, right? Let's take the Graph Heavy as an example. If you check their performance on last human exam, right, very, very challenging benchmark. Graph 4 standard achieves about 38%, and Graph Heavy achieves about 15% higher. By doing what? The same model. They're using the same model, but just using multi-engine architecture. And they price it 10 times higher, right? $30 versus $300 per month. So that's basically the price just for this multi-engine architecture, nothing else. And by the way, DeepThink, Gemini DeepThink is also available now in Google Ultra, also in the highest tier subscription. So I think these are like the most strongest like, commercial evidence I've seen so far about the power of multi-agent architecture. But what if you don't have access to those expensive subscriptions? I have the good news for you, okay? Just if you use MassGen, you can just use any existing API keys you have to any models. You can easily kind of run this experiment of multi-agent scaling, right? You can use a single model with different configurations or mix multiple different models or agents, right, as you want. And how this works is the MassGen orchestrator will take a user's query, distribute that task to the multiple agents and run them in parallel. And the magic happens when there's this shared collaboration hub, right? So all the agents, they can check the real-time updates from others, criticize and refine the results, right? And if some agent finish the work but other agents have new updates, then the agent might get restarted. And eventually they will converge to some consensus and generate the final answer. So that helps refine the quality. And here we can see that the multiple ideas are integrated together. We want to kind of leverage the strengths, unique strengths for different models of different providers and different agents. And we want to run them in parallel to slash the latency. But in the same time, we want the agent to be able to absorb and take intelligence shared from others and improve their own work. Okay? And this iterative refinement keeps going until the consensus. It's very easy to get started. You can simply clone this repo and install some minimal dependencies and get your API keys configured. Okay? And then you can use the CLI to run some configurations. You can configure them differently and try them out. You can either use interactive mode to have multiple turns, conversations, or just ask simple questions. Let's do a quick demo here. So I already have VS Code open and already cloned the repo. So I'm going to try to run the latest version. If you are using the main branch, you may get a slightly different result. Here I'm using a 3-agent default configuration and asking, give me all the talks on agent frameworks in Berkeley Agent AI Summit 2025. Okay, let's run that. Okay, here the system gets started. You can see the question on top and the 3 agents running in parallel. The first agent using GPT 4.0, second one using 4.0 mini, and third one using Grok 3 mini. And you can see all the agents are working in parallel. Some of the agents have access to building web search tools or code execution tools, so they will invoke them when they need to. We can see that some agents already finished work, like the 4.0 mini already provided some answer and have several rounds of voting already. And okay, after the working, we finally selected one agent called the 4.0 agent. Let's see, and the 4.0 agent is doing the final presentation to generate final answer. right? You can see the whole process, and 4 got 3 votes here by the end of the interactions. We can check the output for each agent. Here I enter 1, so let's check agent 1's working process. So this is a log, right? We see that it started with some web search. After search, it generated the initial answer, like this. It found a few talks, some panel discussions, and gave a link to the Berkeley website. And later it has some voting about the agents. Okay. I can also check the second agent, the Forum Mini. Yeah, it generates some answers as it didn't use web search, so it didn't find the right information. Let's see the Graph Forum Mini. Yeah, the initial answer from Graph Forum Mini is they don't have access to the information, but later once it sees other agents' answers, it updated the answer. Actually, you can see another answer provided from here, so it's actually updates the answer. But eventually, it's also voted for all. Okay, and the final answer is presented by for all, and it combines the information from all the different agents. Okay, so that's a simple demo. You can try this out and try different queries. There are a few earlier case studies when we had the first version. So this was using the current main branch. And we tried a number of different examples. For example, we asked agents to find who is IMO 2025 winner, which AI wants IMO 2025. And we can also ask open-ended questions like do some collaborative writing, write a story for like robot music stories. And we can also ask very hard questions like how much does it cost to evaluate Graph4 on the HLE benchmark? This is an open question. You can't find any information online to directly answer these questions. But some agents can find piece of information from the website, and some other agents can use their code execution, data analysis capability to do the estimate. So eventually, the multiple agents can collaborate to try to answer this question. We can also ask questions like travel guide, like if I want to travel to Stockholm in October, can provide a travel guide. Usually, a single agent will find some information, but each of them will find slightly different information, and only when you put them together, you get the best answer. So from this case study, you can see there are several different flavors or reasons why this multi-agent scaling can help. For open-ended questions, usually different agents will have different perspectives, and you really get the best answer from combining them. And for many other hard tasks, it requires many different steps. Usually, the initial answer generated by any single agent is preliminary, but after they see others' work, they get inspired, and they keep refining their work, and you usually get better answers. You can also understand this from another practical point of view. I don't know how many of you like using multiple like AIs at the same time. And when you have a hard question, you try one AI, but you don't really trust the result. So probably you will try another AI and cross-check to make sure you're not fooled, right? So this kind of simulate that automatically, right? By having the multiple agents cross-checking each other's work. But it goes beyond that because it doesn't stop at the first round. It actually try to push them harder, right? To make them further work more. And until they get the final comprehensive answer. So yeah, you can find some of the case studies from the website as well, from the GitHub repo. There's still a lot of, this is like very new, right? It's just a start of this direction. And there are a lot of whole set of challenges ahead. The eventual vision we want to have is to have this recursive scaling so that every time you get a new agent, you add to the system and it amplifies the whole. But we are far from that. So there's a lot of challenges like consensus, shared context, and interoperability, right? We have heard many great talks about addressing these issues. Eventually, we need to solve all these hard problems. But if this really works, then we can have AI that's kind of similar to how we scale ourselves, right? AI can scale themselves too. Yeah, so that's like a very brief introduction about this project. This is like just the beginning. I hope you can check the repo on GitHub, share it, start discussion, join our Discord channels, and build this together. By the way, the new version I just used is coming soon, probably this weekend. Yeah, so I will get a chance to try it out and share your feedback. Yeah, thank you very much. I think I still have time for questions.
So any question for Chiwan's talk? Okay.
Like it can be customized for me running like several coding agents, orchestrating other type of tasks.
Yeah. Great question. Yeah, coding agent is one most important kind of capability I want to integrate into this MassGen. Why is coding a big deal? Because it's a meta power, right? An agent that can change its own software, can self-improve, can experiment, can learn and spawn even new sub-agents. And yeah, you have seen the strong, powerful coding assistant like Cloud Code, Gemini Cli integrated into our developer workflows. And yeah, so but right now they are working alone, right? So the single agent working alone. And if we can iterate that into this multi-agent parallel working paradigm, I think the power will be amplified to large degree. So that's a big next milestone I want to achieve. Great question.
I have a question about like if we have, for example, multiple agent booking a ticket,
Yeah.
so they try to book it all together. How can we ensure that they don't overbook and double book? Or how can we check that each of our tasks whether it's failed or not in a kind of holistic way?
Yeah. This is like it touches very important about like a conflict, or sometimes the agents' work are not easily kind of scalable, right? So that's exactly the kind of the challenges we need to solve, especially when now each agent can go beyond question answering. They also have built-in tools that often can do things. So right now we're not giving the agents that kind of tools. We're only giving them like search, code execution, and they can work in isolation. But as soon as we get to the point where the multi-agent might be working at the same workspace and they have conflict, we have to find a way to resolve that. So that's kind of a great risk question to look at next. Yeah. Thank you.
Thank you.
So I have a great
Thank you.
talk. So I have one question. So in context learning, we have, let's say, some poor quality examples. It might hinder the whole trajectory. So I want to see, let's say, if you have multiple agents and we are scaling up,
Yeah.
and some of the runs are lower quality. So what is your vision? How we can make sure that doesn't like hinder the whole trajectory for the agent?
Yeah, exactly. So actually the demo just shows that exactly, right? So two agents actually provide very poor answers in the beginning. Only one agent find the right answer. And I think this requires some fundamental capabilities to the base models and agents. So each agent has to have a basic way, evaluation capability. So giving multiple answers, it needs to know the relatively better answer for the most of the time. Otherwise, it's not work. I think this built on the assumption that the model has been improving to a point that most of the strongest frontier models have that capabilities. But this is a big assumption that we do need to check. I actually wrote this down in my blog post. I think there are several basic capabilities we need to have. This is one of them. Yeah. Thank you. Thank you very much.
Okay, thanks for Chiwan's great talk. So next talk will be given by Pabi Melo, right? And Pabi Melo is the CPU and the vice president of Cisco. And this talk is about building an open infrastructure for the Internet of Agents. Let's welcome Pabi.
Thank you very much. Thank you all for being here. I'm here to talk to you all about building the next internet, the open interoperable internet of agents. And it was very nice to hear the speakers in front of me actually refer to the need for why we need something like this. So Ranjan mentioned how we need to have semantic communication between agents in order to have truly working multi-agent systems. She mentioned the need to have multi-agent systems that can collaborate and all of that. So this is the world that we are moving towards. And I think it's very appropriate. We are here in the frontier stage. This is the new frontier, the frontier of agentic AI, and more particularly, multi-agentic systems. So I'm going to skip through some of the slides here because I know for this audience, it's probably, the need for agents and so on is probably, old hat. I don't need to belabor the point. But let's talk about why do we need a new internet? I get this question a lot. When I talk about the open interoperable internet for agents, it's like, we already have an internet. Isn't that sufficient for agents to communicate with each other? After all, at the end of the day, agents are just software entities, right? Why can't we just use the internet we have? Well, the reason for that is agents are substantively different from the kinds of software entities that we know, whether it's physical machines, virtual machines, containers, microservices, APIs, what have you. What we have today, the behavioral is largely deterministic. And with agents, we are moving, there's going to be a fundamental shift to move from deterministic behavior to probabilistic, non-deterministic behavior. And that leads us to a need for new primitives, new foundational technologies that can enable this kind of communication, this non-deterministic, probabilistic communication to happen in a way that's secure and reliable. So we need to have new ways for these agents to be able to discover each other, to communicate with each other securely and reliably across frameworks, across platforms. And again, one of the former speakers, Debo, mentioned we are going to have a fragmented, heterogeneous type of deployment models. There's going to be agents running in the cloud, agents running on-prem, and all of them need to be able to communicate with each other. And not to mention, the agent communication is kind of somewhere between. We know how to do, obviously, we know how to do human-to-human communication. We know how to do human-to-machine communication, and we know how to do machine-to-machine communication. But the agentic communication kind of has attributes of both human communication in the sense that it is non-deterministic, probabilistic, natural language-based, multimodal, all of that. But at the same time, in terms of the scale, the speed, the ephemerality of agents, it's close to machine. So you have machine speed, scale, ephemerality combined with human attributes of the types of communication. And all of this is what leads us to the need for this new internet. And so what we are seeing here is really something that is layered on top of the internet that we have today. So a semantic and syntactic layer, and again, the NLIP thing that Ranjan talked about earlier, and the semantic communication that kind of feeds into this need for a true semantic layer that sits above the internet and enables agents to talk to each other. And that's what we are building towards. So without further ado, I'm going to skip past the slide. This just talks about a number of different use cases that you can see. And maybe I'll talk through this just for a little bit. We are talking here about common use cases that need this kind of multi-agent system. Well, before I get into this, let me have a quick show of hands. How many of you here have built an agent? Wow, nearly everyone. This is a great audience. How many of you have built a multi-agent system? Wow, this is great. This is really a great audience. Now, that is unusual. So what I'm talking about here, and I'm not going to ask for another show of hands. I think many of you have built multi-agent systems, but typically a lot of the multi-agent systems being built now are typically built within a single framework. And that's because that's just the ease of how to build it. However, what this slide is talking about is common scientific and business use cases that need agents that are built across multiple frameworks. Agents built on LangGraph, agents built on AG2, agents built on Llama Index, all having to talk to each other to solve a common problem. And this goes from very well understood domains, right? You can think about like an IT app deployment scenario. And for that, this is something that's very near and dear to us. We are Outshift, we are part of Cisco, we are an infrastructure company. This is something that we do. This is our bread and butter. Very well understood domain. And yet, even in this domain, when you think about the end-to-end problem that you have to solve, all the way from the service ticket, which may be dealt with by an agent that's running in ServiceNow, having to talk to an agent that has the customer data for that particular issue, which may be an agent running in Salesforce, and then those agents having to collaborate with agents that know about your physical infrastructure, your network data, your security data, your observability data, all of that, which may be from agents built by Cisco and running on the customer's infrastructure. So all of them have to come together to solve this problem end to end. And similarly, there are other domains, emerging domains like drug discovery, which are powered by agents. And there you have agents that are like general purpose large language model agents, from people like Anthropic and so on, talking to agents that are trained on drug discovery data, and maybe even talking to embodied AI agents that are running physical robots that conduct experiments. So again, the meta point here that I'm trying to make here is, you have agents that need to communicate. Oh, wow, I'm already I am running out of time. So this is the collective that we've built, Agency. I'm very happy to say that a couple of the former speakers are in this collective. So we have IBM Red Hat. It is Agency, AGNTCY. Lot of industry backing for it, a number of startups. I have and it is part of, as of this week, it's part of the Linux Foundation, so it is fully open source. We are on GitHub at agency.org and also on github.com/agency. Please go check us out. I was going to go through the architecture of what we have built out, but suffice it to say, I won't have time to get through this entire diagram. But this represents all of the different stages in an agentic life cycle. So all the way from a common way for agents to talk about themselves to advertise their capabilities, their skills, et cetera, so that other agents can discover them, how that can show up in a directory where humans or agents can go discover what's out there, what the capabilities are, how they can be stitched together and allow communication again at that semantic layer so that agents built on different frameworks, on different clouds, on different platforms can communicate and be understood. And then how all of that can be deployed to your cloud infrastructure with a messaging layer that is optimized for agentic communication. And again, agentic communication has a certain shape to it, if you will. It is multimodal. It needs to be very low latency because there may be a human in the loop. But at the same time, there's large state exchange that needs to happen, one-to-one, many-to-one, many-to-many, et cetera. So all of those communication modes are supported by the messaging layer that we have built out. Again, all of this is open source. Again, another slide that gives the architecture in a very simplified way. This also talks about some of the other pillars of the architecture. There's the identity piece. Again, I could go on that for a long time. There are very unique challenges posed by agentic identity. There's, of course, the identity of the agent itself. How do you describe that? What is the agent allowed to do? But then there's also the principle, the human on whose behalf the agent is acting. And that human has an identity and what the human is allowed to do. And all of that needs to come together. On top of that, agents are autonomous entities. They typically carry out a multitude of different tasks. And depending on the specific task that an agent is performing at any given time, what they are allowed to do may be different. So you have this tuple of agentic identity, the identity of the human principle on whose behalf the agent is acting, and then the task that the agent is performing at any given time. So all of this needs to come together when you talk about the life cycle of an agentic identity. So that's something that we've considered as part of the agency. There's the big vexing problem of observing and evaluating agentic systems. Now, when you talk about, again, I talked earlier about the fact that why do we need a new internet for agents? Because agentic behavior is fundamentally different. They're deterministic. They're non-deterministic. They're more probabilistic in nature, et cetera. What that then means is you need to have strong observability around these agentic systems to ensure that Are these agents doing what they're supposed to do? Are these multi-agent systems actually doing what they're supposed to do? Conversely, are they doing something they're not supposed to do? So all of that, so we have observability and security primitives built into agency as well. I will leave you with this. I know I'm at time. Agency.org, please go check it out. There's a lot of code, all the stuff, the architecture that I described, the code that's behind it, the specifications, a sample reference application that will let you build multi-agentic systems in a true, standardized way using these standard primitives that we've built. It's on. With that, I will wind up here. Thank you very much.
Okay, thanks for the great talk. So next speaker is Jay Roach, right? Okay. So Jay Roach is a senior developer advocate at NVIDIA, and he will introduce building GPU-accelerated agentic workflows. Okay, let's welcome Jay's great talk.
Thank you. Good morning, everyone. I'm Jay. I'm a developer advocate at NVIDIA, where I focus on building LLM application. And today, I'm really excited to talk to you about how to build agentic workflows by harnessing the power of NVIDIA GPUs. So let's start with a quick timeline. We have had single call LLMs for a while now, where you send one prompt and get completion back. In 2024, it was RAG, where you basically do vector stored lookups to pull in up-to-date information. And this year, it's the year of agents, where you stitch multiple LLM calls, tool invocations, and reasoning loops into fully autonomous processes. But the true power of this new paradigm is realized when agents work together. Think of an enterprise ecosystem where there are multiple departments which have their own agents. So in this, but to build these kind of multi-agent system, like for enterprise level, like it's really difficult building this kind of workflows. You might face many challenges, which could be architectural complexity, making different tools from different frameworks work together, and there's also problem with the performance and the reliability. And to solve this problem and to manage these systems, earlier this year, we open sourced a framework or toolkit called as Nemo Agent Toolkit, and it is designed to be the glue for your existing agent workflow. And it does that by using universal descriptors. So what it does is it's basically converts every tool, agent, or memory into a function call. And you can piece this function call together, whether it's LangChain, Llama Index, or something that you have built yourself. So let's take a quick demo about how to build these GPU-accelerated multi-agentic frameworks. So in this case, imagine there's an enterprise with multiple teams, and those multiple teams have their own agentic workflows built with different frameworks. So in this case, there are 3 agents: HR, finance, and IT. And these are built with different agentic frameworks with their specific or relevant knowledge bases for their specific departments. So we are combining these all 3 agents and controlling them using a supervisor agent, which is built with LangGraph in this case. And this all pipeline is built using Nemo Agent Toolkit, which is open source. And this all pipeline is monitored using Phoenix, Arise Phoenix, which is an open source observability tool. And the RAG tool, in this case, is completely GPU accelerated. Vector database is being run on Milvus, which is open source and supported by NVIDIA. Then there's LLM and embedding models are also running on GPUs, specifically on NIM. So it's basically a containerized solution to deploy open source LLMs and embedding models with just a single command. And in order to piece those workflow, you have to simply configure a YAML file where you basically mention all the tools that you have access to. And this is too verbose, but what I'm trying to run here is basically running the entire pipeline by giving it a prompt about, hey, what's the parental leave policy? And once the workflow runs, the supervisor agent recognizes this is an HR query and redirects it to the HR agent, giving you the final response. And on the right, it is Phoenix, which is basically tracing the every step of the interaction with this agentic workflow. So this is it. So the future of complex AI isn't just a single agent, but it's multi-agent working together. And Nemo Agent Toolkit helps you achieve that. And the GPU acceleration is what makes this all real time. So if you like to learn more about what tools we offer and want to stay up to date, feel free to scan this QR code and join the developer program. That's it. Thank you, everyone, for listening.
Thanks for a great GS great talk. Let's move to the next speaker. So next speaker is Nandi Sambroshu. Nandi Sambroshu is a staff scientist at Amazon. And he will introduce evaluating agents that automate complex industrial SOPs. Yeah. Okay, let's welcome Nandi.
Hello, everyone. Good morning. Excited to be here. Great talk so far. So I am a senior scientist in Amazon working on building multi-agent framework for automating SOPs. So it's complex industrial SOPs, which is beyond simple tasks. Is it better now? Yep. So the SOPs are something that human associates follow. They're written by humans for humans, not really meant for machines to comprehend. That's where the additional challenge comes in when we are trying to automate them using multi-agent systems. So they are much more ambiguous, open to interpretation. There is a lot of reasoning going on, diverse tool calling, and then also interaction of multiple agents. So I'll give you an example. So in the shipping industry, it's classifying a product, whether it's dangerous or how hazardous it is. It's a very common problem. So they have to, so associates who make this determination, and not everything can be actually done by ML models. So you need human associates looking at different like safety data sheets or other multiple different data sources and actually making a decision and then classifying it. So how would an agent accomplish something similar, right? So it seems simple for humans. Humans have been doing it for a while, but when you try to have like an agent or multiple agents follow that same set of instructions, there are many nuanced reasoning, and like you have to call the tool, multiple tools with precise parameters and interpret the values. Sometimes some APIs may fail. You still have to orchestrate the whole workflow, right? So that's like from an agent perspective. What about the developer? Like there are many decisions the developer has to make, right? So we need to know whether it's just a simple function calling agent or is it going to be a multi-agent framework, reasoning between steps, how much of it should be in the context, how much of the background knowledge of that org or of that of the documents should be put in a knowledge base. And then the reliability. A lot of the speakers before me have mentioned the costs as a big factor. That how do you make these decisions? That what's more important for that use case? Accuracy, reliability, cost, latency, etc. So there are lots of decisions that a developer needs to make. So where do you make those decisions before you actually deploy your multi-agent system to automate complex industry tasks, right? So we couldn't find benchmarks that were readily available. So the ones that are currently very popular are like Gorilla benchmarks, GAIA examples. They are there are lots of results on these, and LLMs seem to be doing well on these, but the same agent framework in these examples didn't really help with comprehending and automating complex SOPs. So we ended up building a benchmark of our own. So we have this is available on Archive. We'll be posting on GitHub soon. This is a benchmark of like 10 different industry use cases, like starting from customer support, aviation, retail, even healthcare. So we've created SOPs, like long instructions, along with the tool APIs and the code, like a mock. Like the code is obviously a mock of the real APIs, and also data sets. And at every stage, we have had human intervention, like human validation, like a scientist validating the code, the industry experts validating the SOP and the APIs, and the data sets. So it's like, so for a dangerous good use case, you actually have the data set, which has the input and output of every API call, what you expect. So you have the safety data sheet, there are the handling and storage restrictions, etc. So it turns out like building the SOPs was not straightforward at all. It was like a very hierarchical and complex way of prompting and creating these different like aspects, like SOP as well as APIs and data sets. So an evaluation is like much beyond pass and fail. So here, like I'll give an example. So we want to make sure that it goes through the whole execution workflow. So we tried only two paradigms so far, like React and function calling. And as you can see, on an average, it gets 35%, like 70%. 70% actually like successfully executes, and only 35% of them actually have correct answer. So so it's like we have a long way to go before we can actually reach the 97% of human level accuracy. So it turns out synthetic data is powerful. So we want to try out these different agentic applications and improvements before we actually go and test out on real production data sets. And so the key thing is that before automating something with multi-agent systems, there are lots of decisions we need to make. And we need to build realistic benchmarks where we can, we can feel confident on those before moving to like shadow and production. So we invite people to, we also have the benchmark generation code available, so people can build benchmarks, add to SOP bench, so the community can actually keep growing. That's it. Thank you.
Okay, thanks, Nadia's talk. Next speaker is Pushkar Nadkar. So Pushkar Nadkar is a senior principal engineer at Supernova Systems. He will introduce Supernova SN40L and Agentic AI with data flow.
Hi, good morning, everyone. My name is Pushkar Nadkar. I work at Supernova Systems, and today I will talk about SN40L. That's the chip that we've built, and I know how it enables the agentic AI. So I'll not go into this slide. Jay already talked about it, and multiple others have already talked about the journey towards this agentic AI systems. Briefly on this, now we have multi-agent systems, which are basically each agent is having its own context. There are multiple LLM calls that are made by these agents, and they also use tools. Now with this, the user experience have changed a bit because the tokens that are needed for serving such applications have exploded a lot. So the inference providers need to provide these tokens at a very high speed. So we have built a full stack solution for serving agentic AI from RDUs to products like Samba Cloud, Samba Stack, and Samba Managed. We can talk about these products later. Today, we'll focus on SN40L, which is the chip that enables all of these products for us. So diving deeper, each of the products that we have has a rack backing it. And each rack has around 16 RDUs. And these RDUs are basically the inference serving engine that we have. Each RDU has compute, which is in the form of tiles, and the backing memory is HBM and DDR. So the tiles themselves have what we call as PCUs and PMUs. PCUs are pattern memory unit, pattern compute units, and PMUs are pattern memory units. So these units are formed in a mesh, and they form the basis of data flow, which we'll touch later. The 3-tier memory, the SRAMs that are part of the PMUs, the HBM and DDR, form the memory system that will hold multiple models together. Now, what is data flow? So if you see, this blue box is basically the attention mechanism that's there in multiple LLMs. And these attention mechanism can be further divided into multiple operators or kernels. In traditional GPU systems on the left, you have these operators getting inputs from the memory, and then they save the output or the result into the memory once the execution is done. So this forms a stop and go kind of execution, many times bottlenecked by memory bandwidth. Whereas on the right side, you have the RDU, which is basically data flow architectures where these blue boxes are PCUs and PMUs. These operators are mapped onto these PCUs and PMUs, and the input streams, which are this QKV, for example, are just, they form the input stream, and you just let the data flow so that the output result is present back onto the memory. So this spatial execution actually helps to provide a lot of compute density and compute efficiency. For example, Llama 3.18b can be is shown here with multiple layers. Each decoder layer, for each decoder layer, the K1, K2, K3 are actually the GPU kernels that will get executed with a stop and go mechanism. Whereas for Samanova, SN40L, you have just one K0 kernel which will execute in one shot. And these decoders can be further fused into something called as loop decoder with kernel looping. So you have a 3.18b model now just running 4 different executions. So this kind of helped us go from baseline 100 tokens per second. With single decoder, we got to 500 tokens per second, and with temporal fusion or kernel looping, we got to around 1100 token per second for 3.18b. And along with that, there is power efficiency. We can run multiple models on single rack machines, whereas others will take multiple racks to run such models. And for agentic AI, you have multiple applications with multiple models. What happens is traditional GPU system with these multiple models need to be served by separate set of GPUs. Whereas for Samanova, because we have DDR, we can actually serve these models on a single rack where all the models, the DDR is almost like 24 terabytes. So you can have as many models as you want, as many weights as you want, as many fine-tuned checkpoints as you want, and serve from the same system with very low switching latency across the models. So this again shows the same thing. You have one endpoint which is serving all the inference requests, and multiple fine-tuned experts can be served on this system. So this helps with memory efficiency, power efficiency, compute efficiency, and you have much better control, and you can enable complex workflows within a isolated environment in your data centers. So for different models, this is the artificial analysis data. We have all the speeds are mentioned here, and these are the models that we are serving. So multiple models from Meta, Qwen, DeepSeek, OpenAI. So yeah, I had very little time, so I had to rush through all of that, but feel free to catch me. I'm here throughout the day, and you can read about it, try it. There are multiple papers out there about the architecture, and feel free to talk to me. Thank you so much.
Okay, thank you for Pushkar's talk. So next speaker is Xifeng Yan. So Xifeng Yan is a professor at UCSB, and he will introduce transforming agent-based customer service chatbots with declarative programming.
Thank you very much.
Okay, let's welcome Xifeng's talk.
Thank you very much. Thank you very much. Thanks for the invitation. Today I'm going to talk about the need of developing an agent declarative language for easing the development of customer service chatbot. Customer service chatbot has been studied for a long, long time. But we know even with the advance of newest large language model techniques, it is still not well done. Fortunately, we have a bunch of new tools available that can help us to build those bots. For example, OpenAI Swarm system, which can package service functions in each individual agent and then coordinate this agent to finish customer service task. We also have this long-time existing open source community that can help us build help us to build the customer service bot. And there are many no-code environments that can help us to achieve this task. But if we look at those environments carefully, we will see that most of them are program-centric, not agent-centric. Even for OpenAI Swarm environment, we will see that it can package functions in agents, but the agent's definition is distributed in those programs, are buried in Python program. We are thinking that whether we can develop a kind of agent declarative language, so the language just describe what agents can do and their relationship. Forget about the Python code, forget about all kinds of implementation details and optimizations. Just have a pure agent-centric file which describes the domain-specific knowledge for a specific customer service and their business logic. So here I just show you one example that each agent actually can handle FAQ, an agent can handle recommendation, an agent can handle the guardrail, an agent can handle very fine-grained flow, like placing an order, for example. This is a flow kind of program, and then we have agent to coordinate them together, all in one single file. And then the question is, do we really need it? I think yes. If everyone has used the SQL program, you know that how SQL good is, right? So basically, using SQL program, we are able to decouple the program from the underlying system. Same thing here. If we have these ADL programs, we will not just lock ourselves in one vendor. If you are using Rasa to develop a customer service bot, you cannot use features in OpenAI Swarm. You have to redevelop everything in order to use those features. By separating them, we have more opportunity to have an optimized system. And furthermore, in ADL, we actually try to recommend more and more natural language programming. Currently, if we mix natural language programming with this Python program, it is quite hard for the business users to read and understand those programs. And we have to maintain a separate SOP statements and convert those statements to a Python program. That's not convenient. In addition to those benefits, we also see that ADL can actually simplify maintenance and updates. We know after those chatbots have been developed, we always need to maintain it and we need to continuously refine it. And for ADL, we basically add a few natural language sentences. But if you use a hybrid Python program environment, you have to define agent using Python program. You need to define intent. You need to catch those intent and put all these Python code in order to implement those revisions. That is not convenient at all, especially for those professionals who do not understand Python very well. So here I would like to show you where does ADL sit. So on the left side, you will see many very powerful existing hybrid programming and framework like AutoGen and so on. They're very good. They can take advantage of both powerful Python programming library and large language models. But just through a few slides I just mentioned, I hope that I can convince you that there's a room for a declarative agent language, especially at least in the context of customer service. You only need one file. This file can be shared with the business users because they are written in a language very close to natural language, so can be understood easily. Okay. So we developed a prototype, and you are welcome to use it, give us a suggestion, and you all can join us, try to make it happen. Agent declarative language. Thank you very much.
Okay, thank you for Xifan's talk. So next speaker is Taba. Let's just move to the next session. Next speaker is Taba Shah. And Taba Shah is AI architect at Innovator. And his talk is about evaluating AI agents for healthcare scenarios, metrics, and stress testing. Okay, let's welcome Tabasha.
Hello. Hello, everyone. Thank you for joining in. And what I'm going to do today is I'm going to specifically discuss on AI agents and healthcare. Right? Healthcare is one of, I think, the a ripe field, ripe business domain and a ripe sector where AI agents can be used. There is a lot of documentation. There is a lot of bureaucracy involved in healthcare. So it's a great field to apply agents. But healthcare also comes with a lot of responsibility in how we are using these agents. So what I'm going to discuss today is at Innovator, how do we evaluate AI agents, right? So I think till now a lot of discussion has been how to make the best AI agents, but again, the most important thing probably is going to be how are we going to evaluate these AI agents. So okay. Why evaluation? Again, I probably don't need to harp more on that, but starting from the days of good old statistics, evaluation has probably been the most important part of AI, right? And as building models has become simpler and simpler, the challenge of using those models and getting the best outcomes and evaluating those outcomes has become more challenging. And that is what are some of the applications of agentic AI in healthcare across? It is across all sections, right? Patient, provider, payer. You can count from prior authorization, patient experience, claims processing, clinical coding, documentation, care management. I can probably spend a day or two just highlighting what agentic AI can do in healthcare, and it's just how can we scale that. When it comes to evaluating agentic AI, there are three main challenges. One is what we call as scenarios, right? Then there are metrics. What metrics can we use to evaluate them? And lastly, it's about safety, right? How do we ensure that the agents which we are building are safe, right, to be used by the end users who are going to be patients and providers. Scenarios. Agentic AI is no longer going to be evaluated on data points. They are going to be evaluated on scenarios which are evaluated derived from this data, right? And healthcare data sets are traditionally been rare, right? There are some out there like Cynthia, Mimic4, Medline, but beyond that, there are very, very few data sets which actually capture the longitudinal history of patients, right? For example, an example is an AI agent calling a patient to book a referral appointment, right? What are the variances which we need to simulate? Accent of the speaker, medical terminology, educational background, age, and again, there are a lot of variables which we need to simulate, and our approach has been to use grounded simulations, right? So we use actual data plus user research plus LLMs to generate very realistic scenarios, right? And those are the realistic scenarios which will combine both the edge cases as well as the happy path scenarios on which we are going to evaluate our agents. In terms of metrics, what are those metrics which we are going to use to evaluate these scenarios on? Traditional metrics like blue, rug, BUD score, they are typically what we have observed is not very useful, right? Then there is a newer approach where for each scenario, you create a new rubric. So recently, OpenAI released their health bench, where for each scenario, they would have their own rubric, and then they would use LLM as a judge to evaluate the response on that scenario. That is okay for benchmarking, but for actual use cases, real world scenarios, that's not scalable. It's just, there will not be, most businesses will not be having that level of human resources to do that level of scenario evaluation, right? So what has been our approach here? Our approach has been to create a metric taxonomy, right? We have created a entire DAG of what all metrics should look like, starting from the task completion and task efficiency to very task-specific rubrics, right? For example, in conversational agents, one of the key rubric is shared decision making, where we able to arrive at a decision with consent of both the agent as well as the user, right? And then we go right to the component level metrics. Are we using RAG? Are we using code execution in our agents? Are we using tools in our agents? If that is the case, what is the individual accuracy of these components? What is the precision recall of the RAG? What is the word error rate of the speech to text transcription? So again, we are following an entire taxonomic based approach to start from the very top, where we define what is the task completion, the task efficiency, and then going down towards task specific rubrics and at a very core technical component level accuracies. And lastly, across safety, right? Again, some concerns are across the domain, hate, discrimination, abuse. I think that's throughout the agentic AI world, and there is a lot of work going on both in industry and academia on that. Two very, very important safety criteria when it comes to healthcare we have observed is PII leakage and tool misuse, right? Again, this can have catastrophic consequences when we use these agents with our doctors and providers, care coordinators, patients, etc. There are also very specific healthcare concerns like medical misinformation or medical advice. Some of our conversational agents are not supposed to give medical advice. In many cases, like a chatbot or Q&A, they are not supposed to provide medical misinformation. Even if they provide the right citation, the citation might not be credible enough, right? So how do you observe and how do you obtain those criteria and evaluate the medical misinformation is another very important topic of research and execution which we are focusing on. What's our approach here? Our approach here has been to identify what we call as vulnerability nodes, right? Most of the agents and most multi-agent architectures are typically using DAG type of or a graph-based architecture like a LangGraph or OpenAI agents. All of them, they have what they call as a graph architecture. What we try to do is identify what are those key vulnerable nodes. Right? Is it the tool execution node? Is it the code execution node? Is it the web search node? Right? And then for those agents, we have very specific guardrails built. And not only guardrails, we also have a policy-based remediation and detection. Right? So it's not only detecting those deviations which are not allowed, but also on the fly remediating those. Right? So that has been an overview of what our approach has been to create agents which are amenable and can be used in a healthcare domain. So yeah, agentic AI development has scaled a lot with different SDKs, but it's the quality of agentic AI evaluation which is critical in deciding how successful we will be solving in those clinical outcomes in healthcare. Thank you.
Okay, let's move to, thanks Taba's great talk. Let's move to next talker, Samuel Rodriguez. Okay.
Hello, everyone.
So Samuel is the co-founder and CEO of Future Health, and he will introduce automating scientific research with AI agents. Let's welcome Samuel.
Hello. Hopefully this. Great. Okay. Hello, everyone. So I'm Sam. I run Future House, and excited to tell you guys what we're up to. So, oh, wow. Okay. So the fundamental problem that we think about at Future House is that biology is too big for humans to understand. Okay, there are 20,000 genes in the human genome. There are 50,000 different diseases that affect humans. There are 10,000 different cell types in the body. And the rate at which we are publishing papers is increasing exponentially. But we do not have the ability to synthesize all the information in the papers. Right? And as a result, there are $100 million bills lying on the ground. So this is a tweet from back in November by Matthew Kirshner, who's a friend of mine who thinks about drug discovery. Wow, this is just going to keep doing this. Let's try. Let's just. Okay, it's going to keep doing it. We're just going to keep going. So, talking about a company called Trace Neuro, which was founded with $100 million to pursue a new drug for ALS. And if you walk through this tweet, step by step, what you will find is that like they are pursuing a new target, a drug for a new target for ALS that was identified entirely from publicly available data, right? And that insight that comes from publicly available data was enough to go and raise $100 million, right? So how many other ideas are there out there that are lying on the ground waiting to be found that could each themselves be worth $100 million? And so this is basically what we think about at Future House. What if we could automate the process of coming up with discoveries, right? So given some quest by a human, so the quest can be go and find a new way of treating ALS. How do you find all the relevant data, find all the relevant publicly available data, also find relevant privately available data, analyze that data, generate hypotheses, and ultimately come up with experiments that you can run in the lab to come up with discoveries that then allow you to update the quest. And what we want to do is that we want to be able to have agents, AI agents, that do each of these steps autonomously so that we can just go and make all of the scientific discoveries that are out there waiting to be made. So this is basically who we are. So we're an independent nonprofit. We're based in San Francisco, in Dogpatch. We launched in November of 2023. We have about 25 people, which is divided between, we have a bunch of wet lab researchers, we have a bunch of AI researchers, and we have a bunch of software engineers. And we're funded primarily by Eric Schmidt, although we also have large contributions from other people, including Open Philanthropy, most notably, and several others as well. And so I'm going to walk you through a little bit about what we're doing. Obviously, this is a 10-minute talk, and we've been doing a bunch of stuff, and so I'm just going to tell you a little bit. But basically, there are 4 steps to our approach. The first step is assembling data sets that we can use to measure the performance of our AI scientists. The second is building tools for the AI scientists. The third is training them. And the fourth is then validating the discoveries that they come up with. I can only tell you about the first 2 for time's sake, but yeah, we're doing work on all of these in every part of the stack. So first to talk about data collection. So what does it look like to assemble a data set? This is LabBench. This is a data set that we came up with last year for measuring the performance of language agents in biology. And it basically measures the ability of agents to perform some specific scientific tasks that are critical for being able to do science. So on the right on the left is FigQA. This is a figure understanding benchmark. You ask a question like, what is the most likely width of the entire image? You give an image. It has some annotations in it, so you as humans can infer basically what the width of that image is. The question is, can the language models do the same thing? On the right is LitQA. LitQA is like retrieval of specific information from scientific sources. So you make big data sets like this, and then you go and you measure the performance of language models on these data sets. So this is a figure from about a year ago, which means it is hopelessly out of date. But we haven't had an opportunity to update it, and so this is what we have, showing various different frontier models at that time versus humans on the different tasks in LabBench, right? And as you can see, they are all the models all significantly underperform humans. Now, at this point, on some tasks, the models are actually as good as humans, but on many of them, actually, they're still pretty bad. This is OpenAI's own data. From OpenAI and Anthropic and the others all use LabBench for benchmarking their models. And this is protocol QA, which is one of the problems in LabBench, and showing for different models performance on protocol QA. Humans are about 55%, and the best deep research is like 28%, so there's still a long way to go. So once you have a data set like this, what do? Well, the first thing to say is that actually, this plot is highly misleading because most of these tasks, like being a scientist requires you to use tools. And most of these tasks likewise require tool use. But we're evaluating the language models here without tools. So you should not trust this, this is like fine, but this is not the full story. So the thing you have to do is you have to go and give the language models access to tools. So this is PaperQA2. PaperQA2 is our literature search agent. So you take a language model and you give it access to a bunch of tools like paper search, like the ability to gather evidence from the papers, the ability to traverse the scientific literature. At this point, PaperQA also has access to like patents, clinical trials. It can like see figures. It can do all kinds of stuff like that. And then this is what it looks like when PaperQA is running. This is the alpha version of PaperQA, which is, again, probably like 9 months old at this point. You ask it a question like, how has the understanding of amyloid beta's role in Alzheimer's disease changed over time? And then it goes in, it searches for papers. It retrieves those papers. And then it's going to go and, like, within every paper, look for what are the most important pieces of that paper that are relevant for answering the question. Once it selects out the most important pieces, it is going to go and iterate. So it'll search again based on what it found, and then search again, and search again, and search again, and so on, until it is able to come up with an answer. This is similar to what the Frontier Labs have released more recently, like deep research and ChatGPT search and all of these. Similar idea. Key thing is that this, PaperQA is like optimized for the scientific literature, so it has access to full-text scientific papers, for example, which the models generally do not, and lots of other useful data sources like that. But the key question is, once you do this, once you give the models access to tools, how do they perform on the benchmarks that I described earlier? So this is performance on LitQA, which is the literature search benchmark. And what you can see is that, like, before you give the models access to tools, they perform significantly less well than humans. And after you give them access to the relevant tools, they actually perform much better, right? PaperQA2 is much better than humans at finding relevant information in the scientific literature, okay? So that's like that's a benchmark. How does it do in real-world tasks? That's the question we wanted to ask. So we had this idea where, like, there are 20,000 genes in the human genome. Previously, there were only 3,000 Wikipedia articles. So we have this agent that can do literature search. Let's just go and write articles for the other 17,000 genes. So we did that. It took about 2 days. It required us executing PaperQA about 100,000 times, analyzing like 1 million research papers, 15 million pages. Interestingly, there are like 2,000 genes for which there's actually like no information in the scientific literature about them, which is pretty cool. And this is what it looks like. You can go and see the articles at wikicrow.ai. They're not on Wikipedia because Wikipedia is like a volunteer-run organization. It's a little bit hard to work with. But you can see them on wikicrow.ai if you want. And then we had PhD students and postdocs in biology blinded evaluate those articles. And what they found is that there are twice as many errors in the real human-written and human-curated articles on Wikipedia as there are in our AI-generated articles. Like, we just give them articles from both. We ask them to identify hallucinations, blinded. They find twice as many hallucinations in the human-written articles as they do in the AI-written articles. And so this is like the first hint of these agents being much better than humans at doing tasks that are required for science. Okay, so now we're taking this idea, we're expanding it to like the other portions of the kind of scientific workflow, right? So I'll just give, like, this is just a peek at our data analysis agent. It is called Finch. You ask it a question like, what can you tell me about molecular drivers of cancer metastasis? Using the data provided, you give it access to some data, right? And then it obviously also has access to the entire scientific literature. It has access to all kinds of different tools, right? And it goes, and after like a minute or something, it comes back to you with like a full report in which it goes and identifies findings, provides you with a entire notebook that is with all the analysis that's done, a ton of reasoning, makes you figures, and so on. And so we were actually able in May to publish the first paper in biology with a new discovery in which everything that needed to be done in order to publish the paper was done by the AI. Literature search, data analysis, hypothesis generation, experimental planning, like even like making the figures. The only thing we had to do was the actual wet lab experiments. That is called Robin. If you want to look at it, go and look at it. But yeah, so I think I will say data analysis, we are not yet better than humans. We are rapidly improving, and it will happen very soon. And so I think it is just like worth reflecting a little bit on like science is going to change very significantly in the next few years as a result of these agents that are like better than humans at doing the things they need to, doing the things you need to do for science. And it's going to be really awesome. It's going to mean that we can do a lot more science. It will also like change the job of being. It will mean that like being a scientist is a little bit different. But yeah, so stay tuned. If you want to use our agents in the meantime, they are available online at platform.futurehouse.org, and we'll be releasing a bunch more soon. So thank you, everyone.
Okay, thanks for Sammy's great talk. And next speaker is No Chong. Yeah. So No Cong is an assistant professor at Stanford University, and he will introduce from code to cell building AI agents for gene editing, stem cell programming, and beyond. Okay.
Thank you. In the interest of time, I'll just dive in. Really pleasure to be here. Today, I really want to share some of our efforts on building highly specialized, but hopefully towards the generally, scientific agents that really, focus on how can we program genome and cells as cures for a lot of disease that we believe will be highly impactful, for aging, for health, for treating disease. So this is our group. We have a mixture of computer scientists as well as wet lab experimentalists that are working together in the group building AI agents and models. So briefly, we have three parts of the lab. The first two parts focus more on wet lab discovery, building gene cell editing tools, how to program immune and stem cells. And today I want to focus more on the third pillar of our lab, which is building machine learning and AI approaches for exciting medicines. And my thought is like really, as most of us know, right, biology is very the slowest, most painful, experimental scientist field, like we've heard from the speakers earlier. And then even though we have computers, internet, I think the progress of pace of discovery in biology, in medicine, has largely stayed the same. I do believe, as Sam was saying, we have an amazing opportunity ahead to take that from a linear, slow sort of growth into exponential explosion. And this is why we're really excited about using AI models and agents. But the problem is, does AI really understand, or at least the current general purpose AI really understand biology? We believe, as really shown by multiple speakers today, is very hard. Because general purpose LM usually have still problem with hallucination, and we are talking about life-saving medicine. It's really difficult to believe in something that might hallucinate a protein or RNA that doesn't actually work, right? And then there are always a lot of problems giving too many options. But in really scientific research, we need a very specific, grounded, explainable solution rather than a bunch of options or maybe an exam-like answer, right? So, and finally, we think we need to put agents into real action, validating lab, generating these cycles, as we also agree. So our approach to thinking about how to build AI sort of workflows for biomedical innovation is sort of laid out here in sort of a acronym ABC. So A is sort of the interface, which is we think that AI agents will really work with human scientists in a variety of biomedical innovation tasks. But the agents are building on top of a foundation of biological aware, biological specific models, like protein language models. We have been working on RNA language models and other type of multimodality models behind the agent. And finally, to really push the whole field forward, we really believe in the value of getting benchmarks, standards that are setting up across different tasks, complex sort of scientific discovery tasks, as pioneered by many groups, including Federal House, right, as we're studying from Lab Bench. So from these agents, models, and benchmarks, I think we can really push the whole field forward. So I want to touch on three components briefly today in my talk. So starting actually, it may be backward from the benchmark, which I actually think is really critical, even for building an agent that actually we know works. We've been building specific benchmarks such as Genome Bench, where we really take real-world discussion, not from a paper or maybe a random sort of a clip from internet. It's really from real genome scientists in their actual research process. They were discussing science, troubleshooting experiments, and this is thanks to our collaborators over 11 years of collection. We got this benchmark set up, distilled from real human experts when they're actually doing research. And the result of that is we can actually use this benchmark to build really strong reinforcement learning approach, shown here, which we call RL router, meaning that because the ability of different models to perform really well at different tasks, let's say some model might be really good at designing RNA or proteins, some model might be really good at experimental troubleshooting, we realize that we might need two layers of RL, right? You have the typical RL focused on the model, but maybe we can have the RL over RL where we really understand what models are really great at doing specific tasks. integrate almost like a MOE type of approach, where we can raise a router, almost like an open router approach, where we can route the question, the challenging questions, to the best model answers to the task. You can see that the RL router at the bottom really outperforms any of the best reasoning models in this genome bench. So I think this, towards building a specialized, really potent RL approach for science, is going to be greatly accelerating our work in building agents. But it needs to start with a benchmark. And then building on this work, we've started to build agents such as CRISPR-GPT, which was published earlier this week, where we can really use that knowledge, for example, in this case, from genome biology, genomic gene editing, to really improve our performance for anything that related to CRISPR gene editing. And you can see that it outperforms a lot of the best models that we tested. I'll give you an example of how this would work with human. You can see that we can have a really nice interface where any scientist doesn't need to know how to code, how to do specialized analysis, can just use natural language, interact with the agent. And you can basically lay out your task, and the agent really understands the whole context of your own project, your lab, that really can help you build a workflow, as you can see on the right, based on the need and the context of your own research. So as you understand better of your research, you can really start building a complex workflow, as shown here, to help you to do design, analysis, and all the things that you wanted, for a specific domain task like gene editing. And we think that this will be very enabling for people, because you no longer need, for example, the PI to be involved, or you need to find some expert. Anybody can really use the agent, knowing that this is built from 11 years of expert knowledge and know-how. So this is what we think a power is to really scale biological scientific discovery. And so, of course, we want to validate it in real lab. So since this is just published, I won't go into detail, but basically we validated using, for example, a first-year college student that on the first goal of doing genetic experiment, they can achieve 80 to 90% success. We were really happy that on the very first test, everything basically works. And really thanks to AI agents, and there's really no involvement from the professors or the senior postdocs. And building on that, very quickly, we also have been expanding the effort beyond just gene editing. Recently, we'll be working with Dr. Matthew Porteous, one of the leaders of stem cell biology and gene therapy. As you know, Dr. Porteous' work is really behind the first approved CRISPR therapy by FDA, Casgevy, and also Graphite, which is a public company working on stem cell engineering. So we really think that working with the leading expert in the field, we can build very potent specialized agents like stem cell GPT here. This is not yet released, but we're hoping to really validate this agent and release it very soon. It's basically building on top of the work we did before, really give you an expert that help you with everything about stem cell engineering, particularly focus on hematopoietic stem cell and induced pluripotent stem cell, iPSCs. Give you one example. The agent actually can design personalized editing strategy based on, for example, SNPs. As you know, all of us share a lot of DNA sequence, but each of us have some small changes called SNPs that are different. So if I only design a general CRISPR or engineering task, it may not work for another person because of small genetic difference. So to tailor, customize the strategy of engineering a stem cell for each person is really a lot of work for human to do. But with the agent, now we can really say it's almost fully automated, because it takes in personalized genomic information and design strategy based on, for example, the donor's profile for that donor's stem cell. So this is really, we see how we can scale almost any domain-specific, extremely labor-intensive task using agentic workflow, as shown here for stem cells. And finally, one last part is I want to show you that we are very interested in bringing this agentic workflow to a broader scope of tasks in biomedicine. And one of the work that's already been pre-printed and really exciting to have a lot of traction already is the Biomni, which is the open source work really led by Yuri Ashkov's group at Stanford CS, but we were collaborators along with Aviv Regav at Roche Genentech. Is more towards a generalist platform for building these agents for a lot of different tasks. And then we also will be releasing a functional genomics agent called AutoScreen very soon, where we believe that we can use this agent to perform any type of target discovery, functional screening, for example, like CRISPR screens, human genetic GWAS studies, where we can really build a lot of agentic workflow for a variety of tasks beyond just the CRISPR and stem cell. And finally, one last thing I want to mention is that we have found that, as you know, why don't we let AI evolve themselves and try to improve themselves? Like Sam were just talking about, right? Why don't the AI be able to, at some point, get smarter, almost like a real human, right? Learning themselves, almost like an AlphaZero type of approach. So we've been building self-evolving agents like Stella, which is just pre-printed recently with Dr. Meng Di Wang at Princeton, where we really are thinking about if we give the agent access to a lot of tools and approaches, APIs, and very defined benchmarks and tasks, can an agent really evolve their own ability to further improve, almost doing a self-RL? And we found that, for example, even without much fine-tuning or specialized design, Stella can beat a lot of the frontier model like Gemini, even Bellman in some cases, using benchmark, really thanks to Future House's work here. So as basically as we've seen, finally, when we have agents self-evolving, we can now give them more data. So we have been actually using SR glasses and cameras to let the agent see what is actually happening in real lab. And we can see that the agent can now, using VLM, really empower people to understand and guide their lab experiment in real world, rather than just on your computer. So we really believe that this will open up a lot of opportunities. And sorry, I'm a little over time, but one last thing is we do have a concern that how this powerful agent will really impact real life. So we're working on, we just have announced the first biosecurity workshop at Europe this year, and we're really looking for people to be mindful as we're building powerful tools, the security guardrails that we need for dissemination. Thank you very much.
Okay, thanks for Professor Chong's talk. So next speaker is Rose Yu. Rose Yu is an associate professor at UCSD, and she will introduce the grounding foundation models for physics science. And also for the netting talks, you should land for this night. Yeah. After 10 minutes, then as this.
Hi everyone. Seems I'm the only one standing between you and lunch. I'm Rose Yu. I'm a professor at Computer Science Department at UC San Diego. Today I want to share some of the work from our group of grounding foundation models for physical science. So we know that foundation models are very successful and they can enable very smart agents, but still they can make very silly mistakes. For example, if you ask ChatGPT which weighs more, a pound of water or 3 pounds of air, and then you will say 2 pounds of bricks weighs more than 3 pounds of air. Or if you ask Cloud, if I got to the top floor, which is the street level, how many stories does the building have above the ground? And after launching of reasoning, it will still say that the building have 3 stories total above the ground. So one of the fundamental reasons for this phenomenon is that these models are trained purely based on data, so they're only data-driven methods. They lack a framework of physical reasoning. Simply scaling up the model with more data or more compute is not going to guarantee that these models can produce physically consistent and scientifically valid results. Our research on physics-guided AI seeks to address this fundamental challenge by bringing the best of both worlds from machine learning and physical science. So using very efficient inference techniques and expressive models in deep learning, probabilistic models, we can relax the rigid assumptions in physical science and make much more flexible expression of underlying phenomenon. On the other hand, the rich domain knowledge in different physical science and specialized tools such as differential equations and symmetry provide the guardrails for these machine learning models to generate much more physically meaningful predictions. And the ultimate goal is by intertwining physical principles with deep learning methods, we can develop trustworthy AI for science. So now, at the agentic era, agentic AI equips foundation models with various tools. If we think about physical science, mathematical models and numerical simulations are the most essential tools for scientists. Compared to a lot of the agentic tools people are talking about, such as clicking on a web page or playing video games, these tools in physical sciences are extremely expensive. For example, in climate science, when we run climate models to understand the energy transfer from the ocean to the land to the atmosphere, we discretize the entire Earth and solve partial differential equations, and just a single model run would take 6 months. Similarly, for public health, when we wanted to produce stochastic simulations to understand multi-agent movement patterns and forecast the future progression of disease, generating only 100 rollouts would take about 3 hours. So just have a single reward feedback takes such long time. How can we even build agents that can interact with this kind of tool? So that's one of the big challenges here for physical science. These tools are very expensive to run. And then, in order to run these tools, we also need to know the very specialized domain knowledge, because they have very different type of interfaces, API calls, and acronyms. A lot of the generic frontier models don't even understand. Finally, because of the missing physics and the gap between mathematical modeling and experimental data, there's a huge amount of uncertainty in the tools. Even with the exact same initial condition, you will get a completely different outcome, and this type of uncertainty will be further propagated with the internal uncertainty of foundation models. So in our group, we have dedicated a lot of effort in building faster emulators to speed up these complex simulations. For example, we built a state-of-the-art global climate emulator that can speed up climate projection from 6 months to a week. And then this is the first model that can generate stable rollout for 100 years at 6-hour resolution. Furthermore, we help domain scientists in epidemiology build fast emulators for public health that enables 100 rounds from 3 hours to 50 seconds. And now this model is being deployed by CDC to project the future progression of public health. Now with the tools, we need to think about how we can interweave them with scientific agents. Even though these faster emulators can speed up simulation, they're still quite expensive to use compared to some of the common tools available. We have to be very careful about how we should use tools for scientific tasks. When we think about scientists solving a problem, we have these tools such as mathematical models or literature search, and we also have years of training that's stored in the memory of scientists. So we only use tools when we don't know the answer or we are uncertain of the answer, and then we try to solve the problem with our internalized knowledge. So what I want to argue here is that when we use tools for scientific agents, we need adaptivity. Here's the results for different benchmark tasks for physical sciences. And of course, like with tool using, we're going to outperform all the frontier models. But what I want to focus on is that if we force a model to always use the tool, then it basically leads the model to be reliant on the tools and not be able to generalize to new tasks. And furthermore, there's extra cost comes with using this very costly tools. So the model basically needs to learn when to use tool and how to use tool. It's only when they realize that its internal knowledge is not sufficient to answer some of the tasks, answer some of the questions and solve scientific tasks, then it will start to seek external tools and help its knowledge acquisition. Finally, I want to showcase this project funded by DARPA, which is trying to build a generative foundation model for automated climate science. So here, we're pre-training the model with large amount of multimodal data from both large-scale numerical simulations and rich text data from rich literature in textbooks and research articles. We fine-tune this model for a variety of tasks in climate science and weather science, for example, forecasting, counterfactual inference, and scenario creation. What's important here is that we have to ground these models with physical laws. So the technique that we developed is called reinforcement learning with word feedback. And the word that we're developing is based on our fast emulator that can provide feedback based on laws of physics. We can use the uncertainty to guide how the model reacts and use these tools, and then to fine-tune this model specifically for domain tasks. And here I want to show a demo of how Genie works in action. Hopefully it works. That's okay, I can just narrate this over. So what you're seeing here is, okay, that's fine. Yeah, what you're seeing here is the demo of Genie. So we're trying to build a multimodal foundation model for hypothesis generation in climate science. And on the left is the visualization of the Earth. And then on the right is a natural language interface that you can interact with the agent. So we select the weather bench, a forecasting benchmark for 14 days ahead forecasting, and we select the time and the location we want to ask. Then we ask the model to analyze the data and plot a linear regression analysis for the average temperature, surface temperature. And then model basically generate code using the agentic approach by integrating our specialized tools such as geolocator, fast emulator, and climate simulations. So then you can see the model can generate this kind of plot by retrieving the data and do the analysis in the backend. Furthermore, we can also examine what the code is being generated underneath so that we can provide a layer of explanation what is happening under the hood for this agent. So we can also locate any point on the globe and ask the specialized questions. For example, if we click on this area and then ask the model to generate a meteorological report for this condition in this region, and then the model will then synthesize the knowledge in the literature and the tools available to generate the following report. Then we know this is accurate because we're grounding the model with the physics that we have, so it's not completely hallucinating, and we can also examine the code that's model generated to look at the outcome. We can also ask the model to do forecasting. There's a lot of forecasting models out there, but then often require special knowledge to interact with this kind of forecaster. So Genie provides a natural language interface for a system to basically connecting all these available tools like a forecaster and then produce the outcome also in a natural language format. Okay, so maybe I'll just stop here because I'm running out of time. So I wanted to highlight that at the age of agentic AI, the problems in physical science is really proposing the frontier for AI. There's a lot of interesting challenges the current AI system still cannot solve. And I hope everybody can look at this particular domain and all contribute. At the same time, I think the dream, as many of the speakers have alluded to, is that AI and agentic tools is providing new set of gears for AI scientists. By working side by side, we can enable AI systems to be more trustworthy with these physical principles and also use the physical principles to help scientists discover unknown knowledge. Thank you very much. And this is my contact information, and thanks for the funding agencies for supporting this work.
Okay, thanks for Rose's talk. So next thing is about netting talks. So we will use a lot of laptop.
Hi everyone. My name is Hemant. I'm here representing the data science team from Zoox. And we're going to talk to you today about how we use text-to-SQL using a multi-agent collaborative framework to find complex driving scenarios. So a core problem at Zoox that helps unlock our company's vision is to be able to query and search for scenarios that occur in our driving logs. So what is a scenario? If you look at this example here, our robot is approaching a crosswalk, attempting to turn right, and there is a set of pedestrians on the crosswalk. So this is an example of a safety case that we would analyze to see how many times this occurs and different robot behaviors that correspond to safety cases. So the method that we need to do this needs to be easy to interpret for all of our developers at Zoox, and also be able to scale for pretty much any scenario definition that you can think of in our driving logs. So how do we achieve this? So we use a agentic AI system to represent all of these behaviors as singular building blocks, and then combine them together as saying robot relevant, agent relevant features to get the result. So this system guarantees an increase in developer productivity to use agentic AI to generate these SQL blocks. We check the executability of the code to make sure the code is actually runnable and gives you the results. We check the correctness to see if it actually matches what you're looking about. The main thing is interpretability, as opposed to what you might have seen with embedding-based searches, where you use like a vector to search against. It gives you as a SQL, so you can find that. And we also validate the code to make sure that our system actually answers a general set of code. So if you look at an example here, a robot is approaching a crosswalk and a pedestrian is crossing in front. We will split that up into robot relevant, which is approaching a crosswalk, and pedestrian, which is crossing in front. And then we combine that with our agent to give queries for each of those things, and then combine them at the end to give a scenario description. This system helps us to scale up these kind of scenario searches for pretty much anyone in the company, and enables us to search for even more scenarios. Thank you. We are at the poster at the back, and if you have any questions, we'd be happy to answer them. Thank you.
Hi guys, I'm from Amazon Engine. So at Amazon's massive scale, we have thousands of employees using millions of devices on our networks. Behind them are thousands of IT support engineers who keep this ecosystem healthy and running. So our team's goal is to make their job easier and make the system more AI driven. So imagine every device on such a network in a company having its own AI support engineer working 24/7 supporting problems as soon as they occur, or sometimes even before they occur. So we've noticed that, and based on studies, that 80% of the cases that employees face, they tend to self-resolve, but often this is based on static documentation and can only guide users to do what to do, but it cannot perform these actions for them. This can often lead to stale instructions and added friction. When an employee goes to an AI assistant, about 43% of the time they have to still go to an IT support engineer, and of the 57 contacts reflected, only 25% get actually resolved, and the rest flow back into this cycle where they have to go through this cycle again. We propose an edge-extended agentic AI system, which is a multi-agent framework that runs on both edge and cloud devices, collaborates autonomously, and maintains this healthy IT customer support system. It's based on at the foundational level is the data and LLM inference layer, where we have all our chat logs as well as Bedrock to support the inference. On top, we propose to add distributed agent registries with access control that control which agent on each system can have access to which cluster. We have diagnostic and remediation tools through MCP that allow these agents to run code on employees' laptops, and also have adaptive memory for personalization that keeps a record on what's going on each laptop. On the second layer, we have local RAG agents that use like smaller LLMs to give offline support, and client agents for performing these user interactions and planning through this cluster. At the very top, we also have like each device can broadcast its local telemetry and its health status, and also get flight level analytics on the global side. So from a user's perspective, you can imagine they have a desktop app that abstracts out this whole system. But on that app behind the scene, there is a multi-agent framework running that has these important agents, local MCP registries, and a client agent that interacts with the employee. This local cluster can also interact with a global fleet and a global array of agents to solve these larger problems. And that's our problem. For more questions, you can visit our poster just behind the scene. Thanks.
Hello and good afternoon, everyone. I am Sumitro Ghatak, working as an AI architect and thought leader at IBM. So we are building AI agents that are increasingly autonomous, fast, and complex. But what happens when our ability to hold them accountable breaks? So this is a challenge that I call as the accountable singularity, and I feel it's fast approaching. It's actually a technical breakpoint in the systems that could make the current safety paradigms like human-in-the-loop oversight and the central logging computationally and economically unviable. So we need a paradigm shift wherein we move the burden of proof from external observation to intrinsic cryptographic self-attestation, which is essentially the concept of verifiable agency. And that's built on top of three important pillars: immutable reasoning through decentralized ledger, cryptographic proof of compliance through zero-knowledge proofs, and automated consequence through trustless enforcement mechanisms. So this framework actually moves us towards creating a truly accountable AI, but there are some questions that we need to answer, which is like, how can we design efficient zero-knowledge proofs, and what are the crypto-economic models for self-governing and resilient agent ecosystems? So I hope to solve these questions through this research, but I would definitely want to know your thoughts on this. Please visit my poster, which is at the end. Thank you.
Hi everyone, my name is Shubhi Asthana. I am from IBM Research, and we are working on agentic debugging frameworks for LLMs. Internally at IBM, we have a large number of agents being developed in the areas of IT ops like site reliability engineering, finance agents, as well as SWE coding agents. These agents are having issues in complex tasks, causing errors like hallucination, incomplete traces, as well as tool call execution errors. So we have looked at the existing debugging efforts in agents and realized that most of these prompt optimization efforts look at the agent's textual output quality. We have decided to go forward into looking deeper at the execution traces of these agents to understand how systematically and strategically the agents are being executed. For this, we have built a trajectory analyzer, TrajTune framework, which is processing these execution traces, dynamically identifying the errors, and then providing revised prompts within certain thresholds to identify failures such as hallucinations, repeated or invalid tool calls, as well as incorrect tool calling logic. We also have a prompt validator, which is looking at the static errors in the agent's output quality and providing structured format in the forms of React or LangChain format. With our agentic debugging framework, we are able to apply on generalized agents in different domains like finance as well as software engineering, and our framework was successful in reducing the hallucinations that occurred during the different intermediate LLM tool calls. With this reduced hallucinations, we were also able to reduce the number of tokens that were required in the agents that enabled us to try out even for smaller LLM models that provided us higher performance. And most of all, the agents had issues with tool misuse and overloading of certain tool calling functions, which was optimized with the help of our agentic debugging framework. So for more information, please come to our poster, which is at the main stage. Thank you.
Oh, hi everyone, this is Xuan. I'm assistant professor in computer science at Virginia Tech. I'm happy to talk about our recent work on small vision language models as future of agents. So why we need the small models? Specifically, our goal is towards the open source multimodal and the small vision language model agents for real-world applications. There are many specific cases where this is particularly useful. For example, if we are in highly data private domains like healthcare or finance, probably people don't want to pass their data to the centralized, say, OpenAI server. And also in some other cases where, say, you want to analyze data in the air, in space, or deep under the sea, there could be a lot of scenarios where you cannot effectively pass data to the cloud to a more large-scale analysis. So small models can be very useful for these edge deployments in robotics, IoT, and wearable devices. So what's the difference in small versus large models? Especially in the agentic applications, small models still lagging behind in certain abilities like tool usage, reasoning, and multi-agent collaboration. We have a recent benchmark called LLM Think Bench, where we systematically benchmark the small models' reasoning capability versus the large ones, and we have many interesting findings. For example, quantization is the most effective way to preserve many capabilities, but they're still lagging behind in many other things. There are many directions to further enhance small models. For example, if we have training signal, we can have a reinforcement gym environment to further enhance it. Or if we don't have training signal, we can have a self-evolution of the models through multi-agent collaboration. I'll be happy to talk more if anyone's interested in this topic during the breaks. Thank you.
Hello everyone, my name is Zhenzong Tu, Assistant Professor of Computer Science at Texas A&M. So I'm happy to present our work on computer vision agent, which is called 4K agent, Agentic any image to 4K super resolution. So what we want to build is basically a generalist on upscaling any image, including some of the natural images, pet photos, old photos, AI generated images, and some of the scientific image domains, such as satellite images, microscopy, pathology, fundoscopy, and etc. So what we build is a multi-agent system which we have a profile module that you can flexibly select any mode to restore any image according to some customized use cases. And we also build a perception agent that can analyze the image and make a customized plan on how to restore and clean this image. And the restoration agent is to execute the plan and then dynamically select which is the best result for each step. So more specifically, the perception agent is going to use a multimodal large language model with some expert to analyze the distortions and degradation and make a customized plan. And then the restoration agent is going to try a bunch of tools. We have included 60 tools, all state-of-the-art for image restoration. And then we have a score function to select the best results according to the visual perception for each stage. We also have a face model, because face is usually the most important and most sensitive part. So we have a face dedicated model to restore that. And according to this highly complicated multi-agent plan, we have built a generalist that can restore different variations of image domains regardless of the image degradation. So let's show some results, okay? So here, suppose this is a pretty shaky capture. We can restore this to very crystal clear. Yeah, and for example, you have your pet friends. We can restore it to this very good picture. And you have an old photo captured 30 years ago. We can also restore it to very good, some hallucinations though. And here is the AI generated image. We can pretty grain and plan, and we can recover and enhance the details to very good high quality AI generated photo. Thank you very much.
Hi everyone. So I'm Ching from Amazon search team. So today I'm going to introduce a flexible and efficient RL framework for LLM. So RL is the most popular stages these days to fine-tune the LLM after the supervised fine-tuning with the label datasets. It allows you to fine-tune with more enriched signals from the actual world. So there are a lot of infrastructure-wise challenges in the LLM given the complex training capability. And Vero is the open source on 2024 October, and it supports various kind of use cases from the real world. And we have a very large user group from both academia and industry. So here is a feature list for what Vero supported these days. We support various kind of algorithms, most popular modeling architecture, and also to improve the training efficiency on both training side and inference side. We integrated with the most modern inference engine and training engines. So to implement your own algorithm, it is very easy to make a few line changes. So for example, the DAPO is the most recent released version we have integrated in the framework, and that has been proven to be adding additional improvement on some popular algorithm like GRPO. So Agentic is the latest feature already enabled in Vero, which with a full list of features such as the server-based asynchronous rollout, multi-turn conversation, and tooling usage. So given its flexibility and efficiency, I'm talking about Amazon Rufus, which thing I'm working on. It is the AI-powered shopping system in Amazon Web Shopping that helps customer to find the right products, and also we can do a lot of shopping inspiration ideas. To build such a very large-scale model, we collaborated with Vero open source framework to enable real large model training, as well as a shopping assistant. We're able to interact with Amazon Shopping APIs internally, and we build rich reward services to provide signals to enhance the model capability to help customer to get enhanced experience. All right, that's all. Thanks.
Hello, my name is Omer, and I'm an assistant professor at the Washington University in St. Louis. So in this talk, my main message is that the foundational system security principles can be leveraged to provide strong security, privacy, and safety guarantees for AI agents. So we all know here that AI agents, or Gen AI in general, is very capable, but it also has pronounced limitations. It hallucinates, it is susceptible to prompt injection, it also has trouble understanding ambiguous natural language instructions. And in the presence of all these limitations, we cannot really leverage the promising capabilities of Gen AI. And the fundamental issue here is that the Gen AI's robustness is an open problem, and the progress on it from the machine learning or the NLP side has somewhat stalled. So a crucial question is, how do we leverage Gen AI given its inherent limitations? In my research, I tackled this problem, and my main insight is that when Gen AI is integrated into computing systems, it is integrated into conventional software stacks. And this raises a very promising possibility that Gen AI, that system security principles can be leveraged to reliably control the success and failure modes of Gen AI. Another important benefit that this provides is that it is complementary to Gen AI's robustness. So in case a model is tuned, for example, via prompt injection, the whole system won't crash. We can still fall back on the system security principles. And as a lot of computing systems where Gen AI is reliable have the foundation or the basis of systems, so it also has wider applicability across web, AR, VR platforms, and so on and so forth. If you want to discuss more, I'll be here, and you can also reach out to me by email or social media. My contact details are available on my webpage.
Okay, is this thing on? Okay. Hey everyone, thanks for not leaving to lunch yet. I'm Sean from AMD Research. I'll try to be very brief. So as everyone in the room knows, large language models are really good at writing Python. They're good at writing application level code. What they're not very good at, as the latest live codebench GSO benchmark showed us, is they're not good at optimization. Now, what's intrinsically an optimization problem is code for hardware acceleration. So we're interested in NPU because it's new and exciting, but all this is true for GPUs, TPUs, FPGAs, what have you. You need specialized hardware experience, expertise, knowledge of domain-specific languages. New chip comes out, suddenly you need to care about the new data type or a new primitive, something like that, right? It's quite challenging for LLMs. You can't rely on base LLMs to do that. So you need agentic solutions. When you're looking for solutions, you need an eval, like most things, right? So we have a benchmark called NPU eval we built for this purpose. And surprise, surprise, out of the box, large language models aren't very good. It's a challenging benchmark. So if you're looking for a challenging research problem, well, that's one. But yeah, if you want to see how agentic workflows work, we do have a booth upstairs. So we can visit our booth to see a demo how an agent writes code for NPUs. And some shameless advertising, we are hiring, so our group is interested in robotics. If you're interested in physical AI or systems level research for robotics, please do reach out. And we're also always looking for interns. It's a great opportunity to visit Colorado. That's where I started my internship, and now I work there. I live in Boulder. So yeah, contact me if you're interested in any of these things. If you want to learn about NPUs or hardware acceleration for robotics, we're at the booth doing lots of interesting acceleration work. Here's some samples of our recent projects from our tiny group at RAD. If you want to check those out, if you're interested, be my guest. And yeah, visit us at the booth. Thank you very much.
Hi guys, thank you for still being here. This is Bo. We are from Emory University. So imagine a kid is doing a math problem. It's very difficult. For the first time, it may cost him like 30 minutes, 40 minutes, and the kid still cannot do it. But for later, if the kid is doing it for the third time, for the fifth time, he can still do it better. So this is for human. For humans, when we are doing similar tasks repeatedly, we can be faster and faster. This is a human cognitive process. So we are trying to know, can this phenomena still appear for LLMs? So here in this work, we are proposing speed-up LLM to implement and benchmark such reasoning speed-up behaviors. So if we are just doing individual queries for each question, it's no way to be faster, right? Because each question is individual. So we need to add memory mechanism for LLMs. And also, we need to make the reasoning adaptive, which means for those more familiar questions for LLMs, it may cause a lower reasoning cost. So for benchmarking such behavior, we are trying different task similarity from lower similar tasks to more similar tasks. We are trying out different memory method. We are trying out different reasoning method. So the answer to this question is very exciting. It's generally yes. So you can see from these curves, we can see a lot of decreasing curves, which means the LLMs, when it's answering similar questions, its reasoning time can be lower and lower. So there are other key findings. So if the tasks are more similar, then the cost reduction process can be more significant. And also, such phenomena appears consistently in different memory methods, and such phenomena also appears consistently in different reasoning methods. Yeah, that's pretty much. Thank you, everyone.
So we will start the launch session. So however, you can after that we will start at 1 p.m. Okay, thanks.